Okay, so let's look at another example here. We got bank robbers that pushed a 1,000 kilogram safe to a second-story floor-to-ceiling window. They plan to break the window, then lower the safe 3 meters to their truck. Not being too clever, they stack up 500 kilograms of furniture, tie a rope between the safe and the furniture, and place the rope over a pulley. Then they push the safe out the window. What is the safe's speed when it hits the truck? The coefficient of kinetic friction between the furniture and the floor is 0.5. So the first thing we want to do here is a force problem. We want to write out our free body diagrams like this. So right here we've got the furniture with its tension, weight, normal force, and friction. And here we've got the safe with tension and its weight. Now, in this situation, right, if we take a look, this furniture is going to accelerate off to the right, while the safe will accelerate down. Both of them are going to accelerate then at the same rate, meaning our accelerations then are constrained to act in equal magnitude. Okay, the tension in the rope then is where, if we assume that we got a massless and frictionless pulley and a massless rope, then our tensions are going to be the same as well. So for our furniture here, our net force, acceleration, and therefore our positive direction is to the right. For the safe, our net force, acceleration, and therefore positive direction is down. Okay, we always want to set our positive direction in the same direction as acceleration. Now then, we're going to go ahead and take a look specifically at just the furniture to begin with here. Okay. Now the net force on the furniture is going to be equal to the mass of the furniture times the acceleration. So looking along the direction of that net force, we see that the tension minus the frictional force will equal the mass times the acceleration, the mass of the furniture. Our expression then for friction is mu k times normal force equals ma. Okay, and our normal force, in this case, because we're on a flat surface, our normal force will be equal to our weight. This is mass of the furniture. So at this point is as far as we can go with the furniture. So now we have to come back up here and take a look at the safe. So analyzing the forces on the safe, then we end up its net force points in the downward direction. So our tension is negative. Our downward direction is positive direction, and we end up with this MSG minus the tension equals MSA. So what we have now is we have two expressions, and we have two equations for our net force. So if we combine this with this, we end up with this, which is obtained by using elimination. Okay, we add those two equations together and we get this. Putting things all together, we end up with this right here. So now we have an equation for our acceleration. Now we can just plug in our numbers and find our acceleration. We do that and we get 4.9 meters per second squared. Okay, so that's our acceleration of this thing, but remember what the problem is asking for all the way back here is what is the speed when it hits the truck. So using that acceleration, then we should be able to figure out our speed using kinematics. So the kinematics equation we want to use will be the third one here, Vf squared equals Vi squared plus 2a delta y. Now we have to think about this at this point. Okay, when we worked out our solution, when we worked out our forces, right, we set the positive direction as downward, remember, for that safe. When we start looking at kinematics, though, we want to set that negative direction as downward. Okay, so for this kinematics equation, we're going to start at rest, right, but our acceleration is going to be a negative 4.9 meters per second squared down this 3 meter distance. And so we end up with this negative 29.4. Now we have to remember this negative is directional, okay? So it's not a value of that, it's of that velocity, it's directional. So we can simply take the square root of that, and we end up with a final velocity of negative 5.42 meters per second, which is about 12 miles an hour. So it's kind of unlikely that this truck is going to be able to withstand the impact from this 1,000-kilogram safe. Okay, so here's another example. This is an actual problem from an AP test several years ago. Blocks 1 and 2, masses M1 and M2 respectively, are connected by a light string as shown above. These blocks are further connected to a block of mass M by another light string that passes over a pulley of negligible mass and friction. Blocks 1 and 2 move with a constant velocity v down the inclined plane, which makes an angle theta with the horizontal. The kinetic frictional force on block 1 is F, and that on block 2 is 2F. On the figure below, draw and label all the forces on block M1. Okay, so here on this block M1, we have got, in our downward direction, we've got our weight, Fg. We've got, perpendicular to the ramp, we've got a normal force. We've got a rope pulling up on the block, so we've got a tension. And we're told here that this thing is moving down the ramp at a constant velocity. Therefore, we must have a frictional force up the ramp. So we've got a kinetic friction force. So this would be a correctly drawn free body diagram for this without any extra forces or components listed on it. Part B of the question is, determine the coefficient of kinetic friction between the inclined plane and block 1. And we're told here we're going to express our answers to each of the following in terms of M1, M2, G, theta, and F. Which that means is we're not going to plug numbers into this. We're just going to solve in terms of these variables. So now the kinetic friction is given to us by Fk, which is mu k n. That's our kinetic friction. The normal force is going to be m1g cosine theta. We can get that from our free body diagram. So, and here's that free body diagram. All we have to do now is plug in the normal force into our expression for our equation for friction, where we get this, and then simply solve that for our coefficient of kinetic friction, where it would be F over m1g cosine theta. Okay. Part C says determine the value of the suspended mass, capital M, that allows blocks 1 and 2 to move with constant velocity down the plane. We're going to start this by drawing free body diagrams for all three objects. Here's the one for mass 1, mass 2, and the hanging mass. Now what I've done with these is this here is just showing the weight component instead of showing the whole weight. And here, this is big M designating that hanging mass. Okay. Now we've got tension 1, that is the tension in the rope connected to the two boxes on the ramp, and tension 2 is the rope connected to the hanging mass and block mass 2. Now it's also going to be important in this to choose a positive direction as down the ramp. Okay, that's just going to make things easier if we choose the direction of motion as our positive direction. We're told in the problem that this moves down the ramp. And also we need to recognize that we're told in the problem that we are moving with a constant velocity. Therefore, our net force is equal to 0. So then, our net force for block 1 is going to be m1g sine theta minus tension 1 minus the friction is equal to 0. Okay, so for block 2 then, okay, we end up with m2g sine theta plus t1 minus t2 minus 2f equals 0. So that's everything in the positive direction for block 2 and everything in the negative direction. For block 3, we get t2 minus mg equals 0. Okay, and again, this is the direction of motion we set as positive. So for that hanging mass, the positive direction is up. So what we're going to do with each of these three is we're just going to simply combine them. Okay, we're going to add them together. And end up with this big old thing. Okay, now we're just going to work some algebra magic, and we get this right here. So take a moment, make sure you pause, make sure you see how we arrived at this as our answer. There, and then now on to the last part. The string between blocks 1 and 2 is now cut. Determine the acceleration of block 1 while it is still on the inclined plane. And this part of the problem is really actually quite simple. Okay, this block is now going to be accelerating down the ramp. It's going to have m1g sine theta as the down the ramp force and friction back up the ramp. And our net force now is going to be m1a. So our net force down the ramp, m1g sine theta, minus that frictional force equals m1a. And here it is, and we end up with g sine theta minus f over m1. There is our final. Okay, there's the optional video. Those are both really good problems to study and make sure you are prepared for. See you in class.